Hello everyone, I'm Eli Jones from Jackson High School, and today I'm going to be sharing with you some of the research and development I've done towards the synthesis of this new drug candidate, Lindbergin E. So your first question might be, what is Lindbergin E, and why would I want to attempt to synthesize it in the first place? So this is actually the structure of Lindbergin E, and the two predominant reasons why I want to synthesize it is its promising leishmanicidal activity, which basically means it has a certain drug activity towards leishmaniasis, and also its unique structure, which you can see right here. So let's first start off with what is leishmanicidal activity. Well, leishmanicidal activity is basically drug activity against the disease Leishmaniasis, which is caused by the bite of an infected sandfly with protozoa from the genus Leishmania. And what this does is it results in the formation of these painful ulcers or even lethal organ damage. So there are two predominant treatment options for this disease. Unfortunately, because this disease is caused in third world countries, both of these treatment options have their drawbacks. So we're looking for possible alternatives to the treatment of leishmaniasis, so we can treat these third world countries more effectively. And now to the second reason why I decided to synthesize this compound, which was its structure. Its unique structural feature called the PDAP moiety is present in over 16 different classes of unexplored natural products. So this is a moiety that has never yet been synthesized. In organic chemistry, it's very rare to come upon some kind of structural unit that hasn't been synthesized. So it's a very unique opportunity for me. So if I'm able to synthesize this moiety, I'll then be able to apply that to different molecules in the future. Here are three different examples of those drugs that contain this moiety. So if I can synthesize Lindbergin E, I should also be able to synthesize these other drugs. So this is kind of the bulk of my research, the synthetic planning. And what this is doing is this is basically saying, okay, here's a really complex drug structure, okay? So it's kind of like a large mansion or a large house. We have a really complex structure, and we have to figure out how can we break it down to a simpler building block. So in the case of a house, we would figure out how can we break it down into 2x4s and doors and windows. But in the case of my molecule, I'm figuring out how can I break this molecule down into simple building blocks, something we can buy commercially. And this is actually my synthetic plan that I've developed. Here's Lindbergin E right here, the drug I want to synthesize. And I'm going to go over really briefly some of the chemistry of my synthesis. So you can see Lindbergin E is actually something called a heterodimer, which means it's prepared from two uniquely different monomeric units. So this heterodimer gives me the perfect opportunity to apply a convergent synthesis, which not only will give me higher yields, allow me to run two reactions simultaneously, but it will also allow me to basically bring these two fragments together in a final coupling reaction. Because you can see this heterodimer right here has this really weak methylene bridge that holds the two fragments together. So I need to find some way that I can add that in the very last step. And that's just what this conversion or kind of bringing together synthesis allowed me to do, to bring together fragment A and fragment B to get the final Lindbergin E. And I'm bringing that together using something called a three-component reductive alkylation. And here's actually fragment A. Let's analyze that first. So here's fragment A and fragment A. In fragment A, I'm preparing from 3,5-dimethoxyphenol. And the reason I'm doing that and not preparing it from fluoroglucanol, you can actually see I prepare it from 3,5-dimethoxyphenol. These O-methoxy groups are still here, and I just removed them in the end. Why would I not just use fluoroglucanol, right? Because I'm removing the O-methoxy groups in the end. Well, I'm actually using those O-methoxy groups as a protecting group to prevent multiple additions of this 2H chromine unit, because if I add those protecting groups, I'm only going to get one 2H chromine unit, and it's not going to be reactive towards polyalkylation, basically. And this was kind of the fundamental reaction in this whole preparation of fragment A. The preparation is 2H chromine. And then I just do a simple acylation to get fragment A. And then for fragment B, here's the final fragment B. Everything is really typical right here. I'm preparing these two reactions just to prepare the 2-methyl-4-glucanol precursor, basically doing a Vilsmeier-Haack formylation and then reducing that to get the methyl group. and then adding a butanoyl group using a Friedel-Crafts Acylation, and then adding the formal group. And I added the butanoyl group first because it's less reactive than the formal group. And then from here, this is a unique reaction that I'm going to be optimizing in the future. This is an electrophilic aromatic substitution type alkylation. However, in this case, it destroys the aromaticity, but it does leave us some conjugation, which is a stabilizing factor for the formation of this compound. And basically, what I need to do is I need to achieve only monoalkylation. And that's what's so unique about my modification of this reaction, because previous modifications or previous syntheses involved polyalkylation. I only want to achieve monoalkylation. So this is definitely the fundamental reaction in the preparation of that fluoroglucanol-derived asymmetric polyketide, or PDAP moiety. So let's move on to experimental. So far I've actually performed 4 of the total steps necessary for the preparation of Lindbergin E. Successfully prepared fragment A and also the 2-methylfluoroglucanol precursor to fragment B. For the 2H chromine preparation, it was a very successful reaction. I was actually able to scale it up to the 10 millimole scale. Originally, the paper I was getting this from called for a 0.5 millimoles preparation. I was actually able to scale that up 20 times to a 10 millimole preparation, and I had a very successful outcome. I actually got a 95% yield after purification. Here's my 2H chromine right there as an oil. And I had a very clean NMR, very pure product. And then I immediately took that product I had just prepared, and then I acylated that by using butanoyl chloride and aluminum trichloride catalyst. And yes, it's currently present as a mixture of regioisomers, but the issue was basically I wasn't able to separate that adequately using column chromatography. You can see right here I have a lot of overlap of a lot of those regioisomers, so I'm going to use PrEP PLC in the future. And then the Vilsmeier-Haack formylation was also very successful. It gave me a high purity product, triproton anabolic. And then also the Clemmensen reduction of that basically fluoroglucanaldehyde was very successful in preparing my 2-methylfluoroglucanol precursor. And I had a satisfactory yield, but really the key was that I was able to prepare a very pure product. And here's just some examples of the purification equipment I used. And so far, my current results are basically I was able to successfully prepare fragment A, and also for fragment B, I was able to prepare the precursor. And there are still 5 steps to complete for the total synthesis of Lindbergin E, and a lot of these will be optimized in the future with gas chromatography. Thank you. So email me if you have any questions.